Hi, I'm Jerome, and I'm here to introduce you to our submission for the Kaggle Measuring Progress Towards AGI competition, which we call MetaLoop, and it's a benchmark for measuring the full metacognitive loop in large language models. This is joint work that I'm presenting with John Burden and Nora Petrova, and we're submitting it to the metacognition track. And we were interested in whether language models are aware of when they're getting things right and when they're not, and whether that awareness translates into correct behavior. So let me give you some background first. What do we mean by metacognition? We're drawing on the Nelson and Narens framework from the meta-memory literature. And the core idea of it is you have an object level, the actual task you're doing, and a meta level, your model of how well you're doing it. And information flows between these two levels in two directions. Monitoring is bottom up on the right hand side here. The object level informs the meta level, and then control on the left is top down. The meta level adjusts behavior at the object level. And we found most existing work on LLM metacognition only tests one piece of this, usually calibration or sometimes self-correction. We couldn't find a diagnostic suite that aimed to test the integrity of the full loop for language models, and so we decided to build one. Our hope is that this suite can guide targeted training interventions which address a model's metacognitive failures and translate into a more generally intelligent model. Realistically, this is the first iteration of our suite. Our tasks aren't comprehensive, and correspondingly, our findings are tentative. We designed 7 tasks that cover the complete metacognitive loop. Here on the left-hand side, you can see the monitoring tasks, source monitoring, self-review, and consistency, which test whether models can track the quality and provenance of their own outputs. And then on the right-hand side is the control branch, which are tasks 4 through 6, which test whether models can translate self-knowledge into better decisions, betting appropriately, deferring when uncertain, and switching strategy when stuck. And then finally, over here on the far right, the feedback task, the loop task, which closes the cycle and answers the question, can models actually improve their metacognition when given feedback about their earlier performance? Let me walk you through each one. So first, the monitoring tasks. In source monitoring, we gave the model a fictional passage set in a novel domain, then present 32 statements and ask, did this come from the passage, from your training data? Did you infer it, or did you fabricate it? And it's 160 items across 5 passages. And this tests whether the model can distinguish what it read from what it made up, a key monitoring ability. In task 2, self-review, we ask, can the model catch its own mistakes? So we take hard multiple choice questions from GPQA Diamond, MLU Pro, and Regular. And in turn 1, the model answers with step-by-step reasoning. And turn 2, we show its own reasoning and ask it to label each step as correct or error. And this task consists of 153 items. In task 3, the consistency task, we ask, can the model maintain its self-assessment when we reframe the question? So we take the same multiple choice question and present it in 4 different ways. Direct, with a wrong answer suggested, with a correct answer suggested, and in an explanation first way. Then we compare answers and confidence across framings, and this consists of 156 items. So that's the monitoring tasks. Now for the control tasks. There are also 3 control tasks, the first of which is the wagering task. So can the model translate confidence into appropriate bets? The model answers the question with a confidence score, then has to place a bet, safe, medium, or bold, with asymmetric payoffs. And we test 2 conditions, one where the model has to derive the optimal strategy from the payoff table, and one where we tell it the thresholds explicitly. And this task contains 454 items drawn from GPQA, MLU, ARC, Simple QA, and Bool Q. The 5th task, deferral, asks, can the model recognize when to stop or ask for help? And so we present questions at 3 stakes levels, low, medium, high, with increasingly punishing penalties for wrong answers. We also include 138 deliberately underspecified questions where the right move is to ask for clarification rather than guess. So that's 592 items total. And again, there are two conditions: derive the strategy yourself versus explicit thresholds. The final control task is strategy switching. So can the model detect when its approach is failing and switch? We give the model a problem that's been partially solved using a failing approach. The pre-failed reasoning is heading toward a dead end. Then we ask, can it detect the failure and switch to a new strategy? And so this consists of 80 generated problems across 8 task types, including Wordle, Mastermind, Dijkstra task, maze navigation, cipher decoding, and graph coloring. Super. So then the feedback task, the loop task. And this is the capstone task, and it's what makes the benchmark a loop rather than a battery. So we take each model's actual scores from the monitoring tasks, source monitoring, self-review, and consistency, and feed them back to the model as targeted metacognitive feedback. So these are things like you missed 79% of errors in your own work, or your accuracy dropped 39% in third-person framing. Then we retest on fresh items from those same tasks in the same conversation. So the control condition just gets a generic prompt by contrast, which is please try to be accurate and careful. And the difference between the targeted and generic improvement gives us a metacognitive learning rate. And this particular task consists of 140 items. Great, so that's the benchmark. Let me tell you about our evaluation setup. What did we run? So we ran 12 models across 6 providers, and we also collected human baseline data with 540 human participants recruited via Prolific. We got the human baselines for 5 of the 7 tasks: wagering, deferral, self-review, consistency, and source monitoring. And so we didn't get human baselines for strategy switching or the loop, since those tasks required a pre-filled conversation history that didn't translate neatly to a human study. The analog, we didn't really feel it was there. Super. So what results did we gather from our evaluations? I've summarized them in this table here. You can read our write-up for a more detailed exposition on these. So our main findings across the battery. In source monitoring, we found that humans detected confabulations at a rate of 63%, and models weren't totally dissimilar, ranging from 52 to 78%. Both struggled on plausible sounding fabrications, the ones that almost followed from the passage but didn't quite. Then in the self-review task, humans self-corrected at a rate of just 6.6%, and models generally were much higher, ranging from 0% to 59%. So the models were substantially better than people at catching their own mistakes, at least on these hard multiple choice items. Then third, in the consistency task, asking humans to explain first boosted their accuracy by 13 percentage points, and it helped every single participant. Whereas for models, the effect ranged from -19 to +11%. So what I'm saying there is that explanation first actually hurt some models, which I found quite a striking result. Then in the control tasks, so in wagering, humans placed optimal bets 66% of the time, and models weren't totally dissimilar, managing at 45 to 55% of the time. So humans were underconfident and models were overconfident. But when we gave models the explicit optimal strategy, we found that their performance, perhaps unsurprisingly, jumped to being near perfect, hovering around 100%. And so the issue wasn't that the models couldn't follow a strategy, it's that they couldn't derive the correct one from the payoff table. Then in the deferral task, humans spotted unspecified questions 86% of the time at a rate higher than what we found in models, where they range from 10% to 70%. And this is a big gap. Models were much worse at recognizing when a question was broken or unanswerable than the people in our study. In the strategy switching task, we found a pretty wide variance in both detection and correction rates. GPT 5.4, a model that does very well in many other benchmarks, had the worst detection rate at 31%, and Gemini 3.1 the best at 80%, which we found a surprising gap in error detection performance, detecting errors in the prefill. And the correction rates were lower than the detection rates across the board, as you'd expect, since you need to detect in order to correct in this particular task. And those range from 18 to 61%. So even when models spotted, they might have spotted that their approach was failing, but that didn't mean that they could necessarily fix it. Then finally, in task 7, the feedback task, the loop task, self-correction after feedback ranged from 0 to 31%. So targeted feedback did in some cases help models. There's a bit more, to give you a bit more flavor on this particular finding. Models that were good at catching errors unprompted weren't necessarily the ones that learned from targeted feedback. So the monitoring and feedback components appear partly dissociated, uncorrelated. Super, well that's MetaLoop. Thank you very much for your attention. The full code and write-up are available on Kaggle and the links on the screen.